Next topic is lasers and its application. Laser basically it is used as a source and also it has a wide varieties of application in all the fields such as research field, medicine, industry and in defense. In this topic we are going to study the review of spontaneous and stimulated process, Einstein coefficient, that is expression for energy density, and requisites of laser and condition for laser action. Then the types of lasers, there are two types, one is carbon dioxide and semiconductor laser, and at the end we are going to study the laser application, that is in defense. So laser means, the acronym for laser is light amplification by stimulated emission of radiation. So first thing is review of spontaneous and stimulated emission. Now I am going to take for the concept of energy labels. So we are familiar with ground state, excited state energies. So lower energy or most stable state, we can say it is the ground state, and generally it is denoted by E1. And the next higher state, that is called as excited state, and it is having more energy but it is unstable compared to ground state. So in molecular process, if any atom or a molecule which interacts with the matter, then it absorbs the energy. That process is called as absorption and it goes to excited state, and that excited state, it is not stable, and again the molecule tries to come back to its initial state like ground state by emitting the photon, and that process is called as emission. So absorption process and emission process. And emission, there are two types, one is spontaneous emission and another one is stimulated emission. So that will be discussed one by one. First one is induced absorption. So we can define it by the energy level diagram. So E1 and E2 are the ground state and excited state, and generally the initial condition, all the molecules or atoms are in the ground state. So once it absorbed by any energy in the form of light, and it goes to excited state. So the elevation of atom or molecule with the help of external energy to excited state, it is called as induced absorption. So the term induced means it depends upon the external agency. So I can say the induced absorption, it depends upon the number of atoms in the ground state and also energy. Next, emission are of two types. One is spontaneous emission. So emission of photon from higher energy state, that is defined by ES, to lower energy state without any external agency. So here we have shown it by E1 and E2. So this is the transition from higher excited state to lower excited state. That process is called as spontaneous emission. Here it does not require any energy. So because of instability of molecule, it tries to comes to its ground state by spontaneously. So that is called as spontaneous emission. And third one is stimulated emission. Generally the some molecules are in excited state, but it will not come to its ground state because energy is not sufficient. Again it absorbs one more energy and again it will come to the ground state. So transition from excited state to ground state by absorbing one more photon. So this process is called as stimulated emission. So this is not a normal emission because it requires one more energy, or it depends upon the energy. So therefore it depends upon both number of atoms in the excited state as well as the energy. Next is Einstein coefficient, in that expression for energy density. Now let us consider two energy states, say E1 it is the ground state and E2 be the excited state, and consider N1 and N2. N1 and N2 be the number of atoms present in ground state and excited state respectively. Now we are familiar with induced absorption, that is molecular process such as induced absorption, spontaneous emission and stimulated emission. So this is the graphical diagram, energy level diagram. E1 and E2 it is ground state and excited state, and N1 be the number of atoms present in the ground state, N2 be the number of atoms present in the excited state. Initial case If any ground state molecule absorbs energy in the form of light, it goes to excited state, and that is denoted by E star. Further, again the emission is going to take place. So E star, or transition from excited state to ground state, that is called as emission process. Now let us discuss three cases. Induced absorption. First one is induced absorption. Here the induced absorption, it depends upon the ground state molecule and also energy density. If there is no energy, molecule will not go to higher excited state. Therefore, the rate of induced absorption, it is directly proportional to N1. N1 is nothing but it is the number of atoms present in the ground state, and also energy density. Or by equating this proportionality constant, we will get equation 1 as B12 N1 into E mu, where B12 is nothing but it is the Einstein coefficient of induced absorption, where the 1 2, it stands for transition from ground state level to excited state, and E mu be the energy density. And the second case, rate of spontaneous emission. So already we said that the spontaneous emission does not require any energy. Therefore, the rate of spontaneous emission, it is directly proportional to only on N2. Therefore, the on proportionality constant equal to proportionality constant, we get A21 into N2, that is equation 2. Again the same thing, A21, it is nothing but spontaneous emission, that is Einstein coefficient of spontaneous emission, and 21, that stands for transition from higher excited state to lower state, that is ground state. And third case, the rate of stimulated emission. So again the stimulated emission takes place because of energy, external energy. So it is directly proportional to N2 as well as energy density. On equating proportionality constant, we get it is B21 into N2 into E mu. Say equation 3. Now we have three processes. One is absorption process, which is equal to emission process. Emission are of two types, spontaneous and stimulated emission. At thermal equilibrium, so the rate of induced absorption, which is equal to rate of spontaneous emission plus rate of stimulated emission. Now by adding this, we will get B12 into N1 into E mu, which is equal to A21 N2 plus B21 N2 into E mu. Now the rearranging the terms, will get E mu into B12 into N1 minus B21 into N2, which is equal to A21 into N2, or we can find the expression for energy density, that is E mu, which is equal to A21 N2 divided by B12 N1 minus B21 N2, say equation 4. Now the rearranging the equation 4 by taking B21 as common for the denominator, and N2 is also shifted to denominator. So we have E mu, which is equal to, I can take common as A21 by B21. So I have shifted N2, that is denominator. So it becomes 1 divided by B12 N1 divided by B21 N2 minus 1. Say equation 5. And we also know that as per the Boltzmann law, so as per Maxwell statistics, the N1, it is always more in the general case or normal case. So number of atoms which is available of atoms which is more in the ground state. Therefore it is given by N2 by N1, which is equal to e raised to minus h mu by kt, where mu is frequency, or it is denoted by c by lambda. Or I can change it by N1 by N2, which is equal to e raised to h mu by kt. Say equation 6. Now we can substitute equation 6 in equation 5. So we will get E mu, which is equal to A21 divided by B21 into 1 over B12 divided by B21 into e raised to h mu by kt minus 1, because N1 by N2 as e raised to h mu by kt. Say equation 7. And also we know that as per the Maxwell equation, so this is with respect to frequency. So E mu, which is equal to 8 phi h mu cube divided by c cube into 1 over e raised to h mu by kt minus 1. Say equation 8. Now we can compare equation 7 and equation 8 by term analysis. So we'll get a21 by b21 which is equal to 8 phi h mu cube divided by c cube, or also it is proportional to frequency cube, and b12 divided by b21 which is equal to 1, or b12 which is equal to b21. So it means that for laser action it should be induced absorption which is equal to stimulated emission, that is b12 which is equal to b21. Therefore at the end the expression for energy density, it is given by E mu which is equal to A divided by B into e raised to h mu by kt minus 1.